Okay, hey guys, a little wind to the right, I know. We are going to start the second lesson of chapter 7, talking about periodicity, periodic table, behavior of elements, and so forth. The objectives for today's lesson are going to be to identify and define the quantum numbers, the four quantum numbers. I'll explain those in a little bit. Relate the quantum numbers to the periodic table and the arrangement of the periodic table. And we're going to review just a little bit of the history of the periodic table. And then in lesson 3, we'll move on to electron configurations and a little bit more of the particulars. But some of the easy stuff for today. So the quantum mechanical model of the atom is the current model of the atom. There have been several from Democritus to J.J. Thomson's plum pudding model, to the Bohr model of the atom, and finally where we are today, which is the quantum mechanical model of the atom. So by the mid-1920s, de Broglie realized that the Bohr model was not able to be used with other atoms, really. And so Schrodinger and Heisenberg, kind of right before the Manhattan Bomb Project, started visualizing an electron rather than being a particle floating around the nucleus, but behaving like a wave. And so the electron visualized as a standing wave seems to make a lot of sense about their position in relation to their distance from the nucleus. And so this seems kind of bizarre, and it's difficult to explain, but a great way to do it is using what's called a wiggler, or a vibrating string. It's a lab that you guys will do in physics, and there is a kind of a picture of it up here on the right that I boxed. And if you look, this is a vibrating string that is vibrating like this, and it's creating basically two standing waves, or two halves of a standing wave, I should say, one full standing wave. And so what's happening is it's vibrating back and forth. And the fundamental frequency is where it only forms one of those half waves. That's this right here that I'm boxing. And for every doubling of that frequency, it actually produces two of those, peaks, two of those half waves, creating an entire wavelength, which you would see down here on the bottom, or in the middle rather, like this. And so it vibrates up, and on the other side it vibrates down. And then these are the nodes here where the string is actually, it almost looks motionless if you look at the picture at the top. It's quite an amazing lab, and the most I've been able to get is about 9 or so of those standing waves within a certain pattern at a certain frequency. But this parallels the behavior of electrons actually quite well. Anyway, so what we're trying to say here is that first distance from the nucleus would be, say, like the energy level 1 here for an electron that was, attracted to the nucleus. If you look at the second one, this would be sort of like energy level 2, where the electrons are behaving like a wave, and they stay at that certain point, I guess is a way to say it. When you actually use this lab up here at the top, and you turn up the frequency on the dial, between these two right here, there is no wave. The string just kind of looks like this until you get to the right frequency, and then suddenly it levels out, kind of like in music, it's like an overtone. And so what it is, it just forms a perfect, even, this cast double wave like this, or two half wavelengths anyway. And as you increase the frequency between this for the second and the third, again, the string just kind of doesn't look normal. And then all of a sudden, once it hits that next multiple of the fundamental, it levels out, and it forms these three perfect little half waves. The idea is that the electron behaves very similarly and can be found at these distances, or frequencies, so to speak, is in terms of the waves, from the nucleus. And it demonstrates this wave-like nature and behavior of the electron quite well. And so if we think of it in terms like that, these would be the positions where those electrons remain and are located at any given time. Now, yes, can electrons be found in between these? Sure. But are they really stable in those regions? They're not. And so the idea of this standing wave does a really good job of kind of, depicting this wave-like nature of the atom. This assumes, of course, that those electrons have this wave-like nature, but it does explain their behavior and their distance from the nucleus quite well. So if you look at it here, kind of the same thing. In between those standing waves, there is no regular pattern. It's actually kind of a mismatch. And if you look down here, this one has, say, n equals 4 energy level, you would have 1, 2, 3, 4 complete waves. 5, you'd have 1, 2, 3, 4, 5 complete waves. They overlap and they continue this sort of standing wave behavior. But if it's not a whole number, if it's not right on target, you're going to have a mismatch and you wouldn't find an electron there. At least 90% of the time, you won't find it there. You'll find it in one of these stable wave-like locations, I guess is a way to say it. So anyway, it does a really good job of explaining that behavior where the Bohr model of the atom did not. And so what Heisenberg put forth was this uncertainty principle, though. And the idea is that you can't know both where an electron is and the speed of that electron, or you can't know its position and its momentum at the same time. A very simplified way of describing this is you can't know where an electron is without looking at it. And in order to look at it, you have to give it energy, shine a light on it, so to speak. If you do that, you actually cause the electron to move, and now you can't know both. You can know kind of where it's going, how fast it's going, but you don't know really where it is. That's a very simplified way of what he's saying, but he's right. And so we don't know precisely where it is, but we can predict where it is most of the time. And so Schrodinger and Heisenberg were able to put forth this idea, this quantum mechanical model of the atom that says, hey, this is where the electron is 90% of the time, and it makes sense. There you go. And we've moved forward, and that's what we use today. So this is fine for really small, for small objects like electrons, tends to work very well. But for macroscopic objects, like it says there, it's really not relevant. Okay, so there are 4 quantum numbers, and the quantum numbers, we talked a little bit out in pre-AP about this, but they can be used kind of as an address to know where an electron is at any given time. And so I used to live, without telling you my current address, I used to live at 1509 Kernstown Lane. And so the 1509, those 4 numbers would tell you a lot about where I lived. 15 would say it was the 15 block. 9 would tell you I was the 9th house on that block. And the odd number, 9 being an odd number, would tell you I was on the north side of the street. And so the address tells you a great deal about where you live. Here, for quantum numbers, the 4 quantum numbers tell you precisely where the electron is, what shape the orbital that it is located in is. It also tells you the spin direction. So these electrons spin on their axis, not spinning around the outside of an atom, but spin on their axis, and it tells you their direction of their spin. It also tells you their energy level. Actually, that should have been what I said first. But anyway, so I'm going to go through it and do this. I realize that on your paper it's already completely filled out, but the principal quantum number is represented by the letter N. The principal quantum number is that distance from the nucleus. It is that energy level that the electron is located in. And it's going to have numbers of 1, 2, 3, whole numbers up to 7. I guess it could go beyond that, but at least in their ground state, no. So they'll have values of 1 or 2 or 3 or 4 and so forth. I'm just going to do some of these and then I'll show you the picture. The azimuthal quantum number tells you the shape of the orbital that electron is located in. So, and it is represented by the letter L. And it tells you, its shape. So the shapes that it can represent are S, P, D, or F, and we'll revisit those in a little bit. But the spherical or S-shaped orbit is represented by the letter 0, or the number, 0. And so in the first energy level, you can only have S-shaped S-shaped orbitals. But the values for L go from, this is kind of messy. Let me just write it on here and then I'll erase it. But the values for L are from 0 all the way to a value of N, the energy level, principal quantum number, -1. So the possible shapes that you could have in the first energy level, since this energy level is 1, would be from 0 to N-1. So from 0 to 1 minus 1. Well, that doesn't make any sense. That means that you can only have 0 as a possible number for your L value, which means you can only have S-shaped orbitals in the first energy level. And if you were looking at a periodic table, remembering how we did electron configurations, if you went across the S's, there's just hydrogen and helium, so you're only going to have S-shaped orbitals. If I go down, I'm going to tell you a little bit more about that azimuthal quantum number. So in the second energy level, that goes from 0 to n minus 1, correct? So that would go from 0 to 1 because 2 minus 1 would be 1. So I can have the S-shaped orbital and the 1 represents the P. I could also have a P-shaped orbital. If I go down to energy level 3, 3 minus 1 is 2. So I would have 0, 1, and 2. 2 is the new one. 2 would actually represent the Ds. And in 4, you would have 0, 1, 2, and 3. And that 3 actually represents the F-shaped orbitals. So these are possible ones. Now, we're not talking necessarily about, we're talking about a single electron at any given time in an atom. And so what you're looking for is the 4 quantum numbers that are possible to represent an electron in a ground state of a certain element or atom. Anyway, moving on to the third quantum number, magnetic quantum number, M sub L, M sub L, is the orientation. So in terms of a spherical shaped orbit, or the S, which we'll get to a little bit later, it doesn't have an orientation. It's just completely around the nucleus. But with P-shaped orbitals and D and F-shaped orbitals, they have different axes that they're on. So if these were my axes, I would also have, a Z-axis coming in and out of the paper here, or screen, I guess. You would have an X, Y, and a Z-axis. This magnetic quantum number tells you what axis that you're on and where its position is in space, which is quite awesome, actually. And the spin quantum numbers can have values that go from negative azimuthal quantum number, or the negative L value, all the way to the positive L value. So in terms of this first one, energy level 1 right here, would go from negative 0 to positive 0, which is ridiculous. You just have 0. So it's not going to have an axis. It's just going to be a spherically shaped orbit around the nucleus. With the second energy level, you've got P's, right? So it can go from negative 1, also 0, and positive 1. And so you can have 3 different axes, X, Y, and Z, that those P orbitals can be located. If we look at the third energy level for the D, you can have values that from negative L to positive L, whole numbers, negative 2, negative 1, 0, 1, and 2. Now, those are the orbitals that they're located in. Each of those orbitals can house 2 electrons. So those are those 10 electrons that are in the D. You have 1, 2, 3, 4, 5 possible shapes or locations where they are amongst those X, Y, and Z axes. And so this represents those 5 orbitals and where those 10 electrons would be. Could also do the Fs. It would go from negative 3. It would be negative 3 all the way to positive 3. And there will be a total of 7 of those, meaning that it had 7 orbitals. And then the spin quantum number is actually quite simple. There are only going to be 2 electrons in each orbital. And so you're going to have a plus or minus, we say 1/2, so plus or minus 1/2. So one electron represents half of the spin within that orbital, and the other electron represents the other spin in that orbital. This would be a clockwise or counterclockwise spin on its axis, which creates a magnetic field and allows it to move around the atom. So anyway, all of those, of course, will be the same. All the way down the spin is the same. And yeah, and so I'm going to kind of scroll down, let you see, but I know this is already filled out on your paper, but that's essentially what this means. And so if you get beyond energy level 4, all we have right now that I'm aware of, and actually there's quite a bit of debate about D and F-shaped orbitals, but those are the only ones that we're aware of now. So anything beyond energy level 4, we consider just Fs. So it would just be those 7 orbitals at the F. Okay. So this is kind of a really cool image that shows the addition of the electrons as we were, say, adding them to an atom, so to speak, or looking at building what the atom looks like from the nucleus through its core electrons out to its valence or outermost electrons. So I'm going to kind of switch my computer here around a little bit and stop sharing that screen and try to share with you guys this PowerPoint here. Let's see if I can, yeah. Okay, so what I'm going to do is, I'm hoping this will work, but what I'm going to do here is show you kind of the build of the atom. So what I've got here is the nucleus, and outside the nucleus would be the 1s. Now, I can't write with this, sorry, but if you look down here where my cursor is, I've got 1s, 2s, 2p, 3s, 3p, 3d, so forth. what I'm going to do is build an electron or an atom rather coming out with the number of electrons. So the first orbital that's created around the nucleus, or that is located around the nucleus, is the s, the 1s orbital. The 1s orbital can house 2 electrons. And so there we go. We've got a spherically shaped orbital around the nucleus. That is your 1s. Beyond that, if I look down here on the bottom again, we'll get my cursor going. Down there, I have a 2s. So I would have a second shaped, spherically shaped orbital with 2 electrons that surround that as well. And they're getting further away from the nucleus, just like we discussed at the beginning. So I've got my first energy level and my second energy level. I have the 1s, now the 2s. Next is the 2p. And that is within the same energy level, but a slightly increased amount of energy for your p's. And so as I add these, I'd have 1 peanut or p-shaped orbital, 2, 3 different orbitals. Now I'm going to add the electrons to them. And I would have 1, 2, 3 electrons. Notice I'm adding them in each one of the orbitals first. Then I will go back and pair them up. There's your 4, 5, and your 6 p electrons. Now, if we're going across the periodic table, we would do 1s2, 2s2, 2p6, which we've done now through an electron configuration. The next would be the 3s orbital, and that would be housed in it, or would be housed in it, 2 electrons. And so there we're out all the way to the 3s. Next would be the 3p. I can go a little bit further here. I've got 1, 2, 3 p-shaped orbitals in that third energy level. Inside there would be positioned those 6 electrons. Be sure if you're adding those electrons, it's 1 in each orbital before you double them up. There's 1, 2, 3, and then your 4, 5, 6, doubling them up at the end. We'll go one more spot, but if I went to the next, it would be the 4s. It would be a spherically shaped orbit, and it would be on. Now that is showing you where those electrons are located in the build of the atom from the nucleus out to the 4s sublevel or shape. Okay, so let me see if I can kind of stop sharing. We're going to go back to drawing a little bit here. Okay. So you can do it. There we go. Okay, so that was the build. I couldn't get it to work on the iPad while I'm drawing. Sorry about that. But anyway, what we did is we went through and we assigned electrons to this like we did in pre-AP. And we'll go back and we'll revisit that in a little bit. And I'll show you how to do it with the periodic table in case you've forgotten. But your 1s, we added 2 electrons at the beginning, and the 2s, then we added 2 electrons. When we did the p, we added 1 at each time, if you remember correctly. So 1 electron, those are supposed to be upwards arrows, but I'm having, issues. And then you would have the down arrows representing the opposite spins of those electrons, refilling the p's. And we would go all the way up to, I think we went to the 4s. Yeah, we would do the 3s and then each of the 3 p's and then the 4s and so forth. So good. So just to, wrong computer. So just to make sure you guys understand, just reviewing, the shapes are the azimuthal quantum number tells you the shapes, that second quantum number. The spherically shaped orbits will be spheres. So the 1s will be at that first energy level. It will be smaller than the 2s, smaller than the 3s, and so forth. With the p's, there are actually 3 different orbitals. Now, the one that's shown here in the picture, these being your S-shaped orbitals, these in the picture, these are actually D-shaped orbitals, not p's. But if they are within the same energy level, we say that they are degenerate. They have the same amount of energy regardless of whether it's the X, Y, or Z axis. But remember that they do actually fill 1 orbital at a time, 1 electron in each orbital before you double them up. So here are the peanut or P-shaped orbitals. X, Y, and Z axis doesn't really matter. I guess it depends on which angle or what your perspective is looking at the atom as to which one is which. But there are 3. For the D-shaped orbitals, there are 5. I'm not sure why there's a smiley face on that one over there. No doubt that was, 'twas not I. Okay, so fine. There's your D-shaped orbitals. And then the F-shaped orbitals, we can remember the P's as peanuts. They kind of look a little like peanuts. D's, daisies, or dumbbells, I've heard people use as well. F for fancy, if it helps you remember. You do not need to remember any of these shapes, just showing you. I call them funky, but that's okay. And so when we actually fill these electrons, just like we did in the build of the atom, we're going to do it from the ground up. We're going to do it from the nucleus out. So from the first energy level and on up. And And so we need to do a couple of those. So just one reminder about the spin. I talked about it, but here it is with Pauli exclusion principle, is that in a given atom, you're only going to have 2 electrons with the same set of 4 quantum numbers. They could have the first 3 that are the same, but they would have different spins for the electrons within that same orbital. So you would have a spin up, spin down, so to speak, or a spin counterclockwise and a spin clockwise, which is actually better. But they will have opposite spins. And so you assign 1 in each orbital before you go and you double those up. Now, just a little bit about the history, and then we'll finish for today. But originally, the Greeks just said, oh, we have earth, air, fire, and water. So in other words, that desk is just desk. It's just stuff. That changed later, and Democritus said, oh, okay, well, it's made up of atomos, or atoms. There's particulate matter that makes up the matter you're looking at. I couldn't explain it any further than that, but that was a long time ago. Moseley, however, Mendeleev was the next to really, well, not the next, there were several different ones before that, but Mendeleev actually put together the first periodic table. That first periodic table was put together by mass. Now, for the most part, his periodic table was outstanding, especially for the time. But the modern day periodic table notices that there's just a few discrepancies if you use mass as the determining factor for position and placement of the elements on the periodic table. So instead, it's organized by atomic number, or number of protons that each of the elements have. That dictates their behavior far better than how much mass they have. Yes, as you increase protons, you do increase mass, but the neutrons also are a large contributing factor to the mass. And so not having the same number of neutrons is not necessarily dictating their behavior. The protons do. So Moseley later redid the periodic table. This was, I believe, 1900s when it was written in as wrong computer. It was written in as using the atomic number. So once organized by the atomic number, the periodic table really makes a lot of sense. It reflected the organization and the behavior of those elements in their groups and families. We found that certain groups of elements up and down on the periodic table, right? So if I'm looking at this was a group or a family. They behave a certain way. Also, which we'll learn about or be reminded about, you guys learned this last year, but there are trends across the periodic table in terms of certain periods, rather than just groups, families, but also true for groups, families, that there are certain behaviors and we can see from one element to the next an increase or decrease in their behaviors as well. You do need to be familiar with the way the periodic table is organized and what they're called. You need to know what families or groups are. Those are your columns. You need to know what your periods are, your energy levels. Those are rows across the periodic table. The representative elements are located, they're the ones, I say they're always the ones that stick up, but your representative elements are these here. Yeah, mostly S's and P's. And then your transition elements are going to be in the middle of the periodic table, and then the intertransition metals are there on the bottom. So this periodic table, does a great job of showing you where all those are, but try to remind yourself of what those things are. Noble gases you need to know, intertransition metals, metalloids, know where those are too. But yeah, I know that's just strict review. So we're going to quit there today, thankfully. And I'll see you guys on the next video.